Welcome. I'm going to end this week, and in case you're not picking up some of this, I'm trying to move back and forth from the math to kind of the historical and the concept of cryptography as we slowly add in the math for the cryptography. So we're now going to actually start moving into the massive problem, namely the discrete logarithm problem and how that applies to public key encryption. So let's go back to the public key encryption. Let's give an analogy. I always want an analogy because this analogy will actually play a role a little bit later on. So, namely, let's suppose we have two individuals. We have Alice and Bob. Now, in case you don't know this about cryptography, we almost always have an Alice and Bob. Those are that's just because we have A and B and they're sending things between each other. So whenever we have two people sending messages, one is usually always Alice and the other one's Bob. And then usually we have someone named Eve who is the evil person trying to steal our message. So just so you know, whenever you read your book and it talks about Alice and Bob, and this analogy is from your book, but it's a classic analogy that I've seen given a lot of other places as well. So Alice and Bob are always the good people, and Eve is always the person trying to steal it. Sometimes we have a third person who we also have who's also good, and then we have Alice, Bob, and I think it's Carl. But there's Alice and Bob are the most common characters. So just setting that stage so you understand it. So let's suppose for a second that Alice buys a safe. So she has this safe and she puts a little tiny slot in the top, like a slot where someone could slide a note in or something else, money, give her a gift. Not like big enough anyone can reach in and actually pull anything out, but a small slot. If she goes and puts this in a very public place, now Bob can write a message to Alice, come along, drop it in the safe. And the thing about that is that message is now safe because, no pun intended with that, but it's now safe and secure because only Alice has the combination to the safe. Since she's dealing with the combination, she can get it. So if Eve is trying to sneak up and get this message, she has to figure out how to crack that safe. That is where this becomes secure, is because this idea that Alice has a secure safe and Bob simply drops a message in it. By the way, we actually physically do this. I know it's not as physical anymore, but any of you don't know, there are nighttime deposit boxes at banks where you can go and you can drop money and other things like that. Actually, physically do it. I know you can scan in checks and other things like that. But if you're wanting to deposit physical money, or like I do some volunteer work with an organization and help with their finances, and they have to do a massive drop of all the checks and other things. And it's always on a weekend when the bank is closed. And so we have to use the drop box. Now that has to be very secure because you want it tiny enough that someone can't just take tongs and reach in and grab it. The same idea, though, exists in cryptography. We want to create a slot, but it must be small enough that the only thing that gets through is the message. We'll talk later on. There's a question here that will come up later on. It's like, how do I know the message actually came from Bob and not from someone else? That's a whole different question, and we'll get to that. So that's called digital signatures. So basically, the idea here is Alice and Bob have a safe. The safe is our encryption. Okay, so it's where Bob is going to use Alice's safe. So Bob is going to use Alice's encryption, but only she knows how to decrypt it. That's the idea of public and private keys. Now, the most famous of all public and private keys is RSA. Okay. So RSA is actually comes from the name of the authors of this algorithm, namely Art Rivest, A. Shamir, and L. Adelman. They are the three men who published the idea about RSA, and they did so in a paper in 1978. I know that was 46 years ago. It seems like a long time for some of you, but in reality, in terms of the all this stuff they've done, that was crazy. And by the way, they got in a ton of trouble for this. So at the time, the RSA encryption was actually known and utilized, but it was kept private. The NSA actually, for a long time, even after they published this, the NSA would not allow any copies of this paper, which told how to do the encryption, to leave the country. You could not mail it. That was a federal offense. You could not put it in an envelope and take it on an airplane. And so people started having fun with this and actually literally putting the RSA algorithm on T-shirts and then trying to fly through airports with those T-shirts. One person even got it tattooed, and then they tried going through an airport with a tattoo. And finally, the federal government realized they couldn't regulate it. In reality, they didn't need to regulate it. And that's the problem. They didn't realize that they actually had no need to regulate this thing because it didn't matter. This is a public system. This is something that can be used by everyone. They were worried that if it got out, that their enemies could use it against them. They couldn't. So this paper that was so seminal literally told how to create the keys, how the public cipher would work, and it's all based on the idea of again some very old concepts. They're actually from the 1800s. Let's go back 1700s, the 18th century, and it's about the difficulty of factoring from out integers. Remember, I asked you this question earlier. How hard is it to factor? Many of you are like, it wasn't that hard. The truth is, if we get large enough integers, it becomes crazy hard to factor them. Computation, not impossible, but computationally so overwhelming that your computer will not like you. Again, if you give your computer anything that's over like 10 to the like 10 digits and ask it to do things like factoring, exponents, and so forth, it gets really, really upset. It doesn't like it. So for these reasons, this is all safe. Now, to give another visualization, help you understand how the encryption works of RSA, this is again from your book, and it's pretty easy to see. So what Alice does is, let's say Alice wants to send a message to Bob. So she literally can look up Bob's public key. Anyone can see this. Eve, who you can see in here, can see it. She takes that and she is going to encrypt her message using his key. And we'll talk about how that message works. And that will give a new ciphertext. Well, the question is, what happens if Eve, so Eve clearly also knows the encryption, right? If she intercepts this value C, can she, with that alone, do it? Now, in math, this is where the mathematical concept comes. We want something that's super simple so Alice can easily encrypt her message. We also want something so that Bob can easily decrypt it if he knows his private key. We'll call that DB, or decrypting. And if he decrypts it, it gives us back the M. By the way, if you're not paying attention here, this literally means the function that DB of EB of M equals M, which means that these things are inverse functions of each other. So we have to have an invertible function. That goes back to our discrete math days when we talked about what was invertible, what are different kind of functions and their properties and all these other things. All right, I'm just kind of reiterating, working on this. So we have to pick something that's this simple. Now, there's a lot of different public key systems out there. And we're going to talk about a few of them. We're actually not going to do the actual RSA encryption at first. We're going to build up, in part because you can see how the complexity builds in each of the different variations we're going to talk about. So RSA was kind of the seminal paper, and that one still has pretty much held the strength of time. And it's even still continued to use today. It's a common thing in banking. So, and even with RSA, we start mixing RSA with some other encryption techniques as well today, to further make it kind of cool and interesting. But this is how our public key encryption is going to work. But it's also based on a critical concept called the discrete logarithm problem. So the discrete logarithm problem is actually based on simple exponents and solving exponential problems or logarithmic problems. And to kind of see that, let's look at some examples. All right, so I'm switching to a whiteboard because it doesn't really work on the slides to kind of do this visualization. So I'm going to take you back to your algebra days and college algebra and all that stuff. If you wrote 2 to the x power equals 5, how would we solve this? Well, we use this thing called a logarithmic function. And there's lots of different logs with different bases. So one option that is used is that you could take the log, as a reminder, log of base 10, I'm going to write base 10 of 2x is equal to x log 10 of 2. So if we took this thing, so this equation up here, we could literally log both sides. I'm doing air quotes, but you can't see that. And I would have log base 10 of 2x equals log base 10 of 5, which would lead us to x log 10 of 2 equals log 10 of 5. So x equals log 10 of 5 over log 10 of 2. Now, log base 10 or the natural log, all those things are the normal logs. You can also do log base 2. So what is log base 2? Well, log base 2 of 2x is just x. So that would actually just, if I did that to that equation, I'd have log base 2 of 2x equals log base 2 of 5. So that's going to end up giving me x is equal to log base 2 of 5. It turns out that these two things are equivalent. It's called the change of base formula, yada, yada, yada. A lot more information. Not going to get into what that equation is. The point is, we had this really easy way. So if I gave you this function, so all this is again, review from your algebra days. We use this. This is a really easy way to solve logarithmic functions. And we do log actually a lot of things. Natural log is the most common one. And it happens a lot. I do know a number of things, talk about what's the order of something, it's order log and so forth. But this function we can solve if we're talking the real numbers, because log base 10 of 2 is going to be this long, nasty, irrational number. I'm just going to tell you that right now. Because we're asking 2 to what power is equal to 5. Okay, that doesn't make any sense in the real numbers. 2 to any power, well, obviously 2 squared is 4 and 2 cubed is 8, so it's somewhere between 2 and 3, and that's all we know. So what if we modify this problem? We have not been doing real numbers. In case you haven't picked up on this, we've been living in the world of integers, namely doing mod. So let's make this now mod. So I'm now going to make it congruent. And just to make this simple, I'm going to do mod 7. Because if I do this to a prime number, then I guarantee that this, remember, if it's to a prime number, then 2 potentially is what's called a primitive root, meaning it generates all the elements in here. So in that case, if I take 2, so let's just look at the powers of 2. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power equals 8, but 8 is congruent to 1 mod 7. Okay. But that means that 2 to the fourth is 2. And notice we're starting back again. We're just cycling back through. Okay, that's a problem. It actually means if I gave you this problem, this actually has no solution. So this particular problem had actually no solution. Let's change it a little bit. And I wanted to use that example just to illustrate that easily. But what if I change it ever so slightly? Because there is what's called a primitive. Remember, primitive roots are numbers that if you raise them to a power, somewhere in their powers, they generate every other member of that integer, of that modular level. So they create all the values from 1 all the way up to p minus 1. And one of those for 7, it turns out, is 3. So 3 to the x, if we look at the powers of 3, we have 3 to the first power. Well, that's 3. 3 squared is equal to 9, but 9 is 2 mod 7. 3 to the third power is going to be 3 times 2, which is going to be 6. And 3 to the fourth power is going to be 3 times 6, but 3 times 6 is 18. 18 mod, so this is 18, which is the same thing as 4 mod 7. Okay, we're still not there. 3 to the fifth power, well, it's going to be 4 times 3, so that's going to be 12. But 12 is the same thing as 5 mod 7. Hey, sweet, we just found it. In this particular problem, the solution x is equal to 5. It turns out our solution is 5. There's no coincidence, it happens to equal 5. But I could have asked it, this number I was trying to make it equal could have been any of these values. It could have been 3, it could have been 2, it could have been 6, it could have been 4, it could have been 5. And it actually turns out that 3 to the sixth power, we already know that one because it's one less, happens to be 1. So this process, now notice the only way we did this was brute force. We literally had to rotate through all these powers. And in addition to this, this is mod 7. So I only had 6 of them to go through because I only have to raise it to 1 through 6. And even better yet, I don't even need to raise it to the 6th power because I already know what it is to the 6th power because of Fermat's little theorem we did last week. This is why I'm trying to build these ideas. I want you to play with them and think about them because I'm trying to get you to think a little bit deeper. So this one right here is a challenge because all of a sudden, oh, I got a solution, but I had to brute force it. Is there a fancier way to do it? And the answer is yes. And that is where we will come back next week. I'm going to show you how you actually can do it, but this poses a massive problem. And it's why a lot of modern things are based on this, because if you're just trying to brute force it, that's a lot of, not only did I have to run through all of those, but each of those steps has multiple steps because you have to raise it to the next power of whatever I have my base is, and then I have to take it mod p. And because of that, I have 2 steps for every one of these. Potentially it could get uglier. And so it just gets really, really annoying. And if p is really big, this is massively problematic. So this is the idea of from the discrete logarithm problem, and it's the one with which we will be going with. So let me again reiterate what is the discrete logarithm problem. The discrete logarithm problem is we need first g is a primitive root. So again, I need a primitive root. Reminder, that means that it generates its powers, generate all of fp, which fp, remember, is mod p. And h be any non-zero element. That means that h is going to be, remember, there's a 0 element. G does not create 0, but it creates everything else that's non-zero. So we have an h that's mixed in here. Now, on top of all that, the discrete log problem is just trying to figure out what exponent x such that g to the x is equal to h. And we call that the log base g of h. Just like we did log before, the problem is now the logarithmic function that you did before doesn't quite work because the continuous logarithm function and the discrete logarithm function are 2 different problems, and they're both exceptionally hard. Truth is, this one is really hard. All right, that's that for this week. I want you to play with this. So I'm going to give you a couple of problems for the discussion board to actually try to solve this. Again, I'm going to give you small p's. Don't think I'm giving you big p's. And I want you to practice using your exponents, and that's pretty much all you're going to try to do. And remember, if I don't give you a primitive root, then it's going to be slightly problematic. All right, good luck with that.